So AquaStreams. Well, I already gave my introduction, so this is a little bit awkward. I'm just going to go ahead and start talking about the presentation. What's the definition of a stream? What do you guys think of when you hear the word stream?
Non-stop.
Non-stopping. Okay.
C++.
C++. Why C++?
They had last week I've heard it.
Stream library.
Something that flows.
Yeah, flows.
Online processing.
Sweet.
Kind of like no beginning, no end.
What's that?
No beginning, no end.
Yeah, they're potentially unbounded in size. Yeah, there's that analogy, you put your hand in a stream, it's never the same stream. It's so profound, right? So we use streams a lot on the internet. Basically, TCP/IP protocol is a streaming protocol. And in some ways, Reactive Streams mimics that. But we use it to stream video, you know, and react to if the stream can't be sent fast enough, change the sampling. Real-time data sources, if you want to do real-time analytics, streams are useful for that. Large data sets that can't fit in memory, so a good use of streams. Monitoring analytics. Any other examples come to mind for uses of streams important in our day? Or maybe 2,000 years ago, when they would not use streams. Okay. So, so there's some really popular stream libraries out. The Java 7 stream library just released. It's a nice stream library. It supports unbounded in size. It's focused on defining a series of operations. You have a generator and a sink and whatnot. And same with RX Java or RX. Java RX, probably got this transposed wrong. Anybody use either of these? Yeah, experience, comments. What do you like about them? What do you hate?
I used RX in C# and I really liked it.
Yeah.
From what I was using it for, it was awesome.
Yeah. And just like describe a little bit of your paradigm switch. What was different about using streams and how did it fit in your workflows? Maybe some places where streams applied that you didn't initially think of.
Well, so what essentially all the app was doing was it had observed a lot of different type of events. And so C# gives you about 10 ways to create handlers for events. But what RX allowed me to do was it tied it all in, so I had one uniform API, where instead of attaching all these callbacks, I would just have this observable stream that could pass around. That I then, I do eventually attach a callback on with one of their map or one of their transformers, but it just allowed everything to be observable. So it made it a lot simpler in the end. But it was hard to jump to cross that paradigm.
Yeah, it's a little bit weird at first. And I've had this experience where even like doing concurrent programming, sometimes if you do a lot of callbacks or futures and promises, it can get a little bit difficult to track where things are. And when you organize them into streams, you can a lot of times just organize your processes, just think of it as the straight shooting arrow right through, and it provides a lot more structure to processing data. It's a lot easier to reason about. Obviously when that model works, and then maybe you have exceptions where things can trickle off. But Netflix is really hot on the RX library. They use it everywhere. They're the reason why Java RX or RX Java exists. And both of these libraries are great. But why another streaming library? And to answer this question, I wanted to talk first about a problem that I ran into when I looked at both Java 7 streams and RX as potential solutions for this, and was dismayed that they weren't able to solve the problem. So this isn't a very uncommon problem, by the way. So in our analytics system, we have concurrent logging servers that just take JSON messages, react to them, mutate some data in the database to keep real-time counters, but then it logs it all to S3 and compresses them. And I wanted to write a stream. My goal and my with all of this was to be able to model the whole process from start to finish as a stream, where it could be done without any intermittent, like save steps, where the program wouldn't have to stop. I'd be able to go straight from one end, straight into the other, and start writing data while I'm still reading from the source. Related note: if you guys ever like downloaded a 4 gig file and then had to uncompress it, you know that feeling? So another good use of streams, like if you have like SSH or SFTP, you can cat it through and unzip it while it's going through. So you get that same kind of a benefit with where if you have two distinct processes, the downloading of the file and then unzipping it, they're using different resources. Why not overlap them and do that at the same time? You're going to get your file a lot earlier. Well, same for this. If you can like a lot of this, like reading data from the network, processing it, parsing it, and then loading it into the data warehouse, they use different resources. So why do one part of the process while the rest of them are idle? Was my thinking. So to explain again, because I know this font is tiny on the slide, and this is I think my only tiny font slide. So we read these files from S3, we unzip them, we parse them, and we do some like timestamp, like it's semi-structured JSON data. And then we take all this data and we merge it into a single stream, and then we detect the log message type and we dispatch it into different processors, which one of them will do geolocation lookup for IP addresses. There's different steps required to ETL this thing. Bad use of that acronym, but to transform it, and then they all load into different database tables into our data warehouse. And anyways, concurrency is important when you've got this much data, and it's far more data than can fit into RAM. And I looked at Java RX at first, and the implementation of Java RX is purely a push model, and same with RX. So you can only push. Now, quiz time. If this is an asynchronous process right here, and I've got these generators that are just pushing data, what's going to happen? If my bottleneck is here, or here, what will happen?
You'll run out of memory and not be able to process new
Yeah.
requests.
So what are my options? Buffer and run out of memory or drop, or block, and we all hate blocking. It's just never a good answer. Well, and one reason why blocking sucks is because it doesn't work well over asynchronous boundaries, like when you cross network or other machines, etc. So it doesn't distribute well if you're blocking, which is another big issue. And when you've got this much data, distribution is an important thing to think about. So there's this need for asynchronous streams that don't block. They can distribute across nodes and cores, and you don't run out of memory, so it's resilient. It can withstand those things, and that's where the whole reactive word comes from. I gotta be honest. Like sometimes I look at the reactive manifesto and I see the little mobile device, and responsive. I don't fully understand it, but it's kind of a buzzword. But I like a lot of the ideas. So if you understand it, please school me. I'm sure there's a good explanation for it. So there's a lot of different async boundaries, different applications, network nodes, CPUs even. CPUs have to intercommunicate. Let me ask you this really quick. Is it better for a CPU to run 5 tasks in a row and then repeat, or is it better for it to run the same task over and over again? Which one's generally more performant?
Same task.
Yeah. And why?
Because everything's in memory already.
Yes, the program is in memory. You don't thrash your L3 cache, and other various cache levels. So if you want to model your program that way, and you want to have like one step run over and over and over again for efficiency and scheduling processes, like now you've got intercommunicating tiny little programs across an async boundary.
But if it's a pipeline, and you're just like transforming that data along that pipeline, you better for one CPU do all 5 of those steps, right?
No. not always. In fact, it's more likely better to do like 1,000 items in one phase and then
Oh, yes,
1,000 items in the next.
Yeah. Yeah. So you're saying you batch them up.
Yeah,
Okay.
and but still keep it concurrent. You know, maximize the ability to make this thing concurrent. So you want maybe schedule different parts of your stream on different cores, et cetera, et cetera. I'm getting a little too technical now. So yeah, traditional blocking method is a way to get data across an async boundary. With the push method, you get buffering or block or dropping or error, like we talked about. And then the reactive ways, non-blocking, non-dropping, and bounded, and it will solve all of your problems. So how does it do it? These slides that have type safe on the bottom, I ripped off. It's I'll give credit. It was the Roland Kuhn, the type safe guy, did a presentation. I stole a bunch of his slides because I didn't want to do it. So the way this works, it's a really simple idea at the core, and all it is it's a push-pull mechanism where a publisher pushes data up a path, and then the subscriber will send its demand back. And and this enables it to be dynamically push-pull. The system will automatically detect where the bottlenecks are, and it will switch into pull mode or push mode as needed, which is pretty awesome. And this model works when you fork data, if you split a stream into multiple substreams, if you want to load balance it across multiple streams, the demand flows backwards quite nicely. And the other way as well, if you fan in, you can sort of like fan in the data but fan out the demand, right? Which is opposite. So really simple idea. Moving on. So this is the meat of the AquaStream component. It's a very simple API, and this is done so intentionally. So for the publisher, you have a subscribe method. Note it returns unit. That's basically like void in Scala, no value. A subscription just has these two methods, and then the subscriber has the store. It's really, really simple. And the idea of how to get this to work efficiently and how to keep the non-blocking spirit is all calls on the subscriber must not block. So no blocking at all. If it's going to do work, it has to do it, dispatch it to another thread. And they return unit, so that's usually a good idea. If you have something that happens asynchronously, you could return a future with a value, but with as much data as this is processing, could you imagine creating billions and billions of futures? It wouldn't be very efficient. So they just went with unit. And it's subscription must not block, and publisher just, you guys can read. So talking through the activity diagram, when you have a publisher and a subscriber, publisher would be like your data source, right? And then the subscriber might be a map function, or it might be a sync. A sync is where you sort of put the data to be done with the stream, right? Think about water going down a sync. So when you boot the things up, the subscriber will send a message or to call a method on the publisher to subscribe, and then the subscription will get sent back to unsubscribe. So fully asynchronous again, and these are just done with little method calls that happen to return unit. And then subscriber will call request more when he's hungry, and then the publisher will call on next when he's got data. But the rule is the publisher knows how hungry his subscribers are, so he will never push more data than he has signal for the hunger. That's the basic protocol. Yeah.
So help me understand this a little more concretely. If I have an atmospheric sensor that is sending data, I guess my program has a publisher and it subscribes to this sensor's interface, whatever it is. It seems like there would still be some sort of a bottleneck, a physical limitation based on however much cache size that sensor has over the atmospheric data it's gathering, such that if there's a bottleneck later on, it doesn't get told to yep, now go ahead and give us emit your data, then eventually some of that's going to be lost.
Yeah. Okay. So what you're describing there is a really great thing to think about. Great example. So back pressuring a sensor doesn't make any sense at all. It's like, really, you're gonna like go back in time and sense data.
Right.
So there's a lot of buffering options in AquaStreams. And one example we have is, we've been kicking around, is using the project to automatically adjust sampling rate as it detects the buffer. So we'll have a little actor that will monitor the queue size, and it will switch the sampling rate and adjust and react, to use the buzzword, to the sensor being overloaded. We store a lot of data in Redshift, and we bulk insert it. There's only so much you can put in there at a time. So real-time sampling, I think, makes sense. Sampling adjustment would be quite easy to do with AquaStreams. Yeah. Hopefully that was useful. Okay, so as I customly do, it's code time. So I'm just going to walk you guys through a few examples, show you AquaStreams. I built this this little demo project or demo component that will help you to visualize a stream. It renders the stream as a DAG, and I'll just show you. We'll just go. Let me get Emacs on my screen so I can see it. And I'm gonna get, wow, okay, we got some lag here. All right. So we're gonna go through just a really simple flow, and I'm gonna increase the font size. Do you guys know about this Emacs command? Emacs users, it's so awesome. Text scale adjust, meta x text scale adjust. They just added this. I have no idea. It's awesome. Just barely learned that. All right. Yeah. So you guys can all like write it down.
But what it makes what's your resolution, or what makes it magic?
What makes it magic is I don't have to go to this menu
Oh, okay.
and hunt for the font window.
Okay.
That's what makes it magic. I guess I could just use a terminal, but I get crap for that. All right. So this is I'm going to be writing in Scala. This library is implemented in Scala. Although it's not a Scala-specific library, it works with Java. They have Java bindings, and there's a lot of collaboration to get this protocol implemented in a lot of languages. So this is not an effort to convert everybody to code in Scala. Although if it has that effect, I wouldn't mind so much. So let's just talk through this. It's really simple. Actually, I'm going to delete one piece of signal that you don't know yet. Who's good at reading code? Somebody just want to volunteer and read that and take a stab at what it does?
Iterate over something 1,000 times.
Yeah.
Check if it's prime. Print it out, and then when you're done, shut it down.
Yeah. Man. Gentleman and a scholar right here. Thank you very much. So it actually will, it's sourcing a sequence. 1 to the 1,000 creates a range, and it basically ships each number incrementally down the string. The filter is prime method will take only the, okay, yeah, it's basically English, right? I mentioned I wrote this little program to visualize the stream. I had to slow it down because it would send out data so fast it would crash my browser. So I've already got all that planned for. You guys don't need to worry about that. We're not going to have any live demo fails today. So, oh wait! This isn't a fail.
This is intentional.
So there's no browser output. I meant to do this. So it outputted as a word. I think it printed every prime number to the console up right there. I'm pretty sure that those are all prime. Anyway, so the stream works. Yay. Now, this thing I deleted is just this little, it's using the decorator pattern. It's just something I came up with that will introspect the graph and render it to the browser and then send out activity so we can actually watch it do its thing. It's going to be really exciting. So, there we go. So we got a generator pushing out 50, all right. This is the number of messages it pushed out. That's the rate at which it's processing. This filter component, that's how many messages it has emitted. So the messages that didn't pass the filter are not counted in that. And then that's the rate it's emitting messages. And then this for each block, which powers this print line over here, is the sink. That's so we call this the source and the sink. In stream speak, that's what we nerds call it. Pretty straightforward, right? Let's get a little more interesting. So let's take and calculate the sum of all prime numbers. So there's a method for this. Right after filter, if we just put on a fold and do plus. What's that?
Never mind.
That actually looks that looks kind of funny from this angle. So that's the underscore is just an anonymous variable. I could rewrite that as you know, a b is equal to a plus b, but it's just shorthand. So we're gonna get each prime number, fold it into 0, add them all together with the reduction, and then we'll print out the result. And let's go ahead and run that. So you can watch it over here run, and then the output will be the terminal. Oh, I can make this window bigger. So not too exciting. It's going to go up to 1,000. And then, bam, we got our message. So the sum of all params is that. Cool. So let's step it up a little bit more. So our is prime is artificially slow. Let's make that sucker concurrent and see if we can speed this up a little bit. I'm going to process 10 times as many messages because I'm feeling brave. What we can do here is, like, we don't want to do each individual element in concurrent in a separate thread because that would be a whole lot of scheduling nightmare, and you'd lose a lot. You'd have a lot of your CPU devoted towards just work stealing with the fork join queue. So rather than just asynchronously map every is prime, or you call that, why don't we batch it up into sets of 100 and then process those concurrently, just for the example. So first function or directive we'll invoke is or declare is the grouped group directive. That'll take 100 items and then yield down that in a set. And then we're going to map async the sucker. And we're going to put, so our numbers get yielded here. That's going to be a sequence of numbers. And we're going to return in a separate thread, numbers filter is prime. And then now we've got a sequence of let's see what we've got. Error. So we've got a flow with a sequence of integers, and in order to fold those, we're going to need to flatten that and just get a stream of integers again, and that's pretty easy to do. So we're going to do map concat identity. Somebody want to reason with that?
So is
Why
there
would that?
Will there be a flat map async though?
There's not a flat map async. You could have every combination of flattened async, async unordered. I think you'd get into Cartesian expansion land. And so, yeah, you gotta do two. But
So is that basically flattened for streams in this case?
yeah.
Okay.
So the contract of map concat is it yields a sequence, and then it's expected. No, actually, it yields an item. We happen to have a sequence in our string, right, at this point. So the contract is that the function should return a sequence, or list, or vector, whatever. Like sequence is the base type, right? And then it will iterate through each of those and emit each item downstream. So it flattens it. It's like a flat map or a flattened.
So you fanned out and then you come back in.
Yeah. And we fanned out so we could process 100 of these as primes in parallel.
So map concat will apply the function you pass it to everything before it concats them, and you're just passing it identity because you really just want to concatenate.
Well,
Or is
let me write it like this. So, can you read okay? Is it big enough font?
Yeah.
Large
Can you
enough?
scroll the window down a little bit?
Yeah. Oh, I forgot about the heads. Sorry.
Yeah, that's right.
Sorry, I'm clearing my throat. We asked for no pizza or no cheese on the pizza. That was the only option, and might be doing that tonight because I had some. So, map concat. Map async is returning a future with a list of numbers. And async will go ahead and it'll unwrap our future for us, and it'll push that sequence of numbers down the string as soon as that's completed. And there's a map async unordered. If you don't care about the order, it'll just push the first one down. But map async is ordered. And then map concat takes that sequence of numbers and just returns it, and the behavior is it's just going to iterate through it. Am I killing this?
Right. Well, you have a. So you're getting from the map async. It's going to give you.
And then this is just going to be an int. So it's actually a source.
So it's a source of sequences of integers, and you want to concatenate each of those sequences together
To get a source
into your stream.
Yep.
Okay. So there's not just a concat.
Or a flatten. No, there's not.
Huh.
There is a flatten, but it's only for streams of streams.
Okay.
Again, type explosion, right?
Yeah.
And the thing's still under development, so they're still adding features, and maybe they'll add that. Who knows? But presently, no. So now that we have a string, or now we have a source of integers, we can reduce that, add it up, and then output our result. And let's run this. Okay. So we reason about this real quick. Generator is pushing the 10,000 items through, right? It's on 3,200. And then we take a group of 100, so you should expect that to be about that number divided by 100. So those are our groups we yield. And then map async is processing those groups in parallel. Notice how this jumps by about 4. So it's doing 4 groups at a time, and it's just pushing them straight down the stream. So we've got concurrency. And then map concat is expanding those to our fold, but this is filtered. That's why these numbers are so different. So these are the number of primes we found. I was thinking, why didn't they know that? So there's our stream, and our output is this really large number. So sensible enough? Cool. We can keep going. Now let's think a little bit about. I want to show off back pressure a little bit. So one of the cool features about AquaStreams, Reactive Streams in general, is you can have a bottleneck anywhere in your pipe, and it doesn't matter. The system will automatically adjust and keep in pace, even if the part where the blockage is a pure stream component to another thing that's processing much faster. So it just schedules it, and it almost feels like magic. So just as an example here, this is going to be a really contrived example, and not that any of these are that realistic anyways. So first of all, we're going to split our string. So we've got some integer, and we're going to group it by whether or not it's a multiple of 5. And then we can actually
well, I'll explain this in just a bit. True mults of 5, and then case false, others. So this group by will yield a stream of streams where, because it actually doesn't know how many streams to generate as it's going along. You could have potentially an unbounded number of substreams that it generates. And this is actually a pretty cool idea. But in this case, we know we only have 2 because it's true or false. And for every value where this returned true, it's going to yield a stream of just those values. So we can process those independently. And then vice versa with the others. And the reason I did this is because I wanted to create a scenario where it was unbalanced. So we're going to have 4 times as many messages going through this stream as this one. And we're going to put a bottleneck in there and then do our little visualization and watch what happens as we move that bottleneck. So, mults of 5 map. It's basically the identity function, but I'm just going to put a thread sleep in there. So if I do a sleep of 10, it should be able to do 10 messages a second. And then return the I. And then in our other stream, we're just going to do others.map identity. And the map identity wouldn't be necessary, but it wouldn't visualize very well if I didn't have it up there. And then let's combine them. We can do a merge unordered. And then, I don't know, do for each println. And then shut it down. Anybody lost by this?
Where's the mults of 5 coming
You
Oh,
have to declare the
okay.
streams, or is it just-
Glad you asked.
from? Yeah, explain.
This is pattern matching and using value extractors. It's a form of destructuring in Scala. So rather than declaring a normal function, I'm declaring a pattern match. And in the case, the word case, that this first parameter of the tuple is true, it's actually going to yield the value of the second parameter of the tuple. And it knows to do this because true is a reserved word, not a variable name. But anyways, I can see why that might be confusing. So it's basically a parameter will be yielded here if the first part of the tuple is true. The group by yields a stream of tuples.
Okay.
That makes sense.
Okay, I'm really glad you asked. Thanks for that feedback.
And so the count of the mults of 5 and others, that's going to be different based on how fast they're respectively processed.
Well, it's going to be deterministic at this point because our group by function is deterministic. So we should get the same amount at the end, no matter what. But the rate of processing will be the interesting bit.
Okay, so the others and mults of 5 always have the same amount, you're saying? In their batches?
This represents 20% of the value space.
Yeah.
And this represents 80%. So we're going to see 4 times as many values here than we will there.
So is it your group by that's splitting the streams?
Yes.
Or is it the map that splits the streams?
It's actually
based
group by.
on-
Group by creates them. And it yields a stream of streams.
A stream, and each of those streams is
Yeah, so the
Stream of
type would look like this. It's a source, group by thing, or group by value, and then the flow.
okay.
So I map that so I can transform this tuple. I can access this inner. Oh wait, I screwed up. Hang on. It's actually like this. So it's a string of a tuple where the first parameter of the tuple is, or first item, is the value of the grouping, and then the second one is the flow
Yes.
for all values where that is the case. All right. So let's run it. I hope you guys like this visualizer. Okay, so First item you probably noticed is we got 3 things here. Why? It was the best way I could visualize this and not lie to you guys. So,
The exceptions?
no. Actually, in my first incarnation with this visualizer, I hid this, but it's a lie. So I brought it back. So group by is the thing creating it. Remember how I said group by yields a stream of streams? So this stream right here, see how that's 2? How many items are in a Boolean set? Okay, yeah, so that represents the 2 streams it yielded. And that goes into merge unordered. Merge unordered takes that stream, subscribes to the result of all these maps, and then brings those in, resulting in a source of integers. And this is the reason why I colored these arrows red. So the red arrow indicates that it's a substream. Does it read okay?
Yeah, that's great.
Okay, awesome. So it's still processing. Generator still chugging along, and we're having about 10 per second. I blame the drops on the browser because I'm actually measuring the performance in the browser. So our bottleneck is clearly right here, but see how this is running at a nice 40? So it's keeping pace proportionally to the amount of data it's receiving, just automatically. So we won't, basically what's happening is this thing's getting blocked, it's sending back pressure signal up here, and this is only sending data for the minimum of demand.
Are there times when you have to modify or deal with how the back pressure is sent? Do you have to tweak that?
You can. So I mentioned there's a lot of options.
Do you find yourself having to, or is it just like, oh, you if you really want to get yourself into trouble in your experience?
I mean, the majority of cases for which I'm using the project, the standard back pressuring is the ideal.
And what's that default?
Well, it doesn't block. It sends signal upstream so that the generator won't run as fast. So there is absolutely 0 blocking in between these components.
But in the case of an external system that you don't control, in that case, like the default.
It actually has there's a TCP protocol, and this works over network protocols as well.
Assuming that they're speaking the same stack, right?
Naturally. Yeah. I mean, you could buffer on TCP alone because TCP has buffering signal. And I mentioned earlier, these ideas aren't very new. This is basically the TCP protocol brought to stream processing.
And TCP does back pressure maybe. Yeah, TCP's got back pressure built into it.
Yeah. So we're not one-upping TCP in any ways. It's just copying a great protocol. All right. This thing's almost done, but I think we got the idea. What would you hypothesize will happen? I'm gonna get some water. Apologize, guys. Gotta blame the pizza girl, or not her, but the pizza place. Order cheese-free pizza. Oh well. So what would you hypothesize will happen if we move our back pressure from here to here? What would you infer the rate of this component to be?
If you move the back pressure?
Yeah, the blocking, the bottleneck. I'm going to move that sleep call.
Should be flipped.
So this should be about 10. What should this be about?
40.
No. Because it's getting 1/4 of the data.
It'd just be 2 or whatever.
2.5.
That's fine.
Yeah. Kind of a trick question. All right. And there we have it. So it evens out about 10. You can get 10.5, about 2.5 over there. So pretty cool, right? Great. So let's go into a little bit more of a complex example and really watch this thing shine. I tried to get a TCP protocol version working for you, but it's actually having a little bit of trouble with it. So that's milestone 2 release. Give them cut them some slack, I guess. So I'm going to run this shipping example. We're going to step through this step by step. It's a big one. and then I'll open it up for questioning and whatever. Not that we haven't been doing questions already. So this is a basic process that I came up with, and it actually maps really closely something I'm doing in the real world, but not with packages. Names have been changed to protect the innocent. So we have this process where you have various decision points, and sometimes the decision point may yield an answer that this has already been decided, so there's nothing to do at this step, just skip ahead. And part of the process, so sticking with the shipping analogy here, is you don't have infinite space to store packages, right? Like, because they take up space, and space is expensive to some degree. So you want to be able to move packages out, just about as fast as you're putting them in. You don't want things to accumulate too much in one area. So, streams sounds like a good idea. And also, if the work has already been done, we don't want to wait for anybody to search the package, in the queue. Just go ahead and send that sucker right ahead if there's no work to be done on it. So we don't want to be waiting more than is necessary. And at each point, we've got this decision point. Has it already been? Oh, sorry. One other thing. Back pressure is also important here because if we're trying to do overnight shipping, it stands to reason that we probably shouldn't take on more than we can reasonably handle, right? So it's kind of a cool example in that regard as well. All right, back to the example. Back to the decision point. So has it already been labeled for hazardous? And this means yes or no. Yes, no, or unknown, right? So if it's not unknown, we're going to just go ahead and ship it on down. Otherwise, if it weighs more than 40 pounds, like say it doesn't fit on our sensor machine, then that means we got to manually search it, and that's going to be slow. Otherwise, we're going to put it through an automated scan, which is a lot faster and can be done, inline, and we don't have to send it off to another team that just opens packages and looks for hazardous waste and then puts them closest we can. All right, then we take the results of all that and all those packages and put it through our next decision point. Has it already been labeled fragile? If yes, go ahead and skip it on down here. No, can we just do a quick glance and see is something fragile in there? Just look at like one or two of the items. And if there's a yes on that, we know the answer. If it's a no with a quick glance, then we got to search it, and that's another time-consuming process. So the goal here is to label it hazardous and fragile, and then group them by these categories: hazardous, and fragile, and standard. And then we're going to put them on different crates and ship them out. And these different crate types have different capacities for shipping. Like the hazardous and fragile is the most scarce resource. Standard we can do anytime. You get the idea. So I've already done the honor of creating some ridiculous data. We've got these little packages, and the contents are these words. We tell if it's oh, this is terribly small. Let me do my magic trick. So we tell if it's fragile, if it's got art or glass in it, and then we tell if it's got drugs, then it's hazardous or something. And it's sort of a loose idea. And some of these are already labeled. Some of these are already labeled. So they just, maybe the person, when they dropped off the package, it was searched on site, and so we already know that, no reason to redo that effort, right? But then in this one, there is no hazardous tag or fragile. Fragile.
Can I ask where you came up with these words? It's like classic.
Random selection of Shakespeare words. Yeah, I kid you not. I think adultery made it in here, so there's a lot of adultery in this. Maybe that one didn't make it. Anyways. So here's the first part of our process. I've modeled it already, and so we don't have to type it all out. But let's just walk through it step by step and reason about it. So there's this big nasty ugly line using the Java API to search the file system for files, right? So there's 4 files. I'm going to take all 4 files. I'm going to start with the first one, pull its contents. When I'm done, go to the second one, pull it, etc. Right? So the first thing I do is I start with a source of my batches. And batches is just a list of files. Then I'm going to map each of those files and turn it into an auto-closing line iterator. So this first time somebody requests an item from that, when it wakes up, it's going to open up the file and start yielding it, and when it's done, it's just going to close its door on the way out. Then I'm going to take, I actually yield the source, which is not entirely obvious right there, but so I make that it's actually a string of the streams. So yeah, I'm going to iterate through the lines, but it's a stream of streams, so we need to flatten it. And now for isn't there a flatten? Yes, there is. So I'm going to call the flatten operator, and give it the concat strategy. So in the end, I'm going to be reading from all 4 files, but what will be exposed through the stream is just a single line at a time. So I don't have to worry about that complexity anymore. Then I'm going to parse it as JSON and use my cool little library to load that into a package object, which is fully typed. So there's a ceremony. Now to our story. So our first query, volunteer, you want to read through that? Somebody raise your hand. Kirk.
So if the package has the hazardous tag and it's not empty, and go to
Yeah.
the section of the code that says has hazard label.
Yeah. Yeah, and the non-empty, you want to explain that?
It's just you're just ensuring that it isn't an empty list. If it isn't,
It's an option,
oh yeah, it's
actually.
not.
So
Okay.
non-empty means it's unknown. It's like
Yeah,
basically
actually,
checking to
it's-
see if it's null rather than true or false.
So if has empty is a property of your JSON object,
Yeah.
basically.
And then we're going to come down and handle our first decision. So if it does have a hazard label, we're not going to do anything with it. We're just going to do map identity. And again, you don't really need to do flow map identity. You could just return flow, but my visualizer breaks if it doesn't have a node to show. So that's why the map exists, okay? That's my fault, not AquaStream. And then if there is no hazard label, we've got another decision point. Kirk, you want to continue?
Okay, so taking the flow, goodbye. So you're calling the if it fits into the hazard scanning machine, and you're sending it the package itself. So I'm guessing that has some kind of silent attribute. And if it does, you send it. If it does fit into it, the if is going to send it to the sensor testable, and then otherwise it's going to send it directly to inspection inquiry.
Yeah, great. And
Same as above.
I mentioned this one. This one's really expensive. Like, think about this step. You got to send it off to another team, and they just open packages all day and look at the contents and close them. It's kind of a silly idea, but that's why that's map async unordered. Map async unordered, and the unordered bit will tell the workers not to return. It's not first in, first out. It's first in, and then first to be completed out. Does that make sense? That's the map async unordered, because we don't really care about ordering. We care about speed. And then, the other one's just going to put the label. So we're going to merge that decision point and then merge this decision point. And then we're going to output the packages. And let's run that so far. So we can get a nice visual on this. Here I go. Oh, what happened here? I must have hit a key or something. All right. So here we go. We talked earlier, there are 4 files on the file system, right? So that's represented by each of these generators. Anybody want to take a stab at what that is?
So, guessing from your earlier one, it was like the parameters that said, okay, here are the 4 generators that you need.
Yeah, that's my stream of files. Yep. So it could be unbounded. I could be like scanning a file system and yielding them as they come and then just start to operate on them, right? Pretty cool. So I mapped 4 already, and that's why I got the 4 generators. And now I'm calling flatten concat. Look how it moved over to this one. By the way, the coloring's pretty cool, right? That's part of that. It actually detects like the max rate, and it has a little sliding window, and like makes the greenest thing the most hot item on there. It was red earlier, but if you're colorblind, sorry. It's green because it's going. Okay, enough of that. So yeah, the flat concat, you can actually see that behavior. As soon as this gets to 1,000, there's 1,000 items in each file. This flatten is just going to switch its source and start reading from the other generator. And 3, 2, 1, just like that. Kind of cool. So that's flatten concat. So here's our first decision point. We do that group by things with no hazard label. Go through here for our further decision point with inspection needed or sensor testable. And things that already have their hazard label, just sort of skip the whole thing and go straight to here. So you can visualize that, it's kind of fun. And then inspection needed is going through that map async unordered. So that's like the team of peons whose their only job is to open packages and look for hazardous waste and then shut it. Be a terrible job. And then, yeah. And then right on down here, we're doing a for each output. And you can see the output here. Let's scroll and check this out. So this package has repeats, insufficients, and shock. Not hazardous. But this package right here was labeled hazardous. Has organs. Yeah, human organs. My glass. Who the hell is packing this stuff? All right.
I think it's piercers.
So cool. We got our first step, and now everything that comes through here, whether it had a label or not in the beginning, now it has a label. And the mechanism we got that, and this has real world implications. Like you might be processing data, and there might be a machine or like some predictor you use where you can predict pretty accurately that you can just make the decision on your own, or maybe it's ambiguous, and so you assign it for a human being to review, and you could use these same types of ideas. So moving on, now we're going to do the fragile label. Really same idea. Do you want to read it? Just go ahead. Hey, go ahead. You go ahead. Yeah, that's my hunch. All right. So run this again as soon as this recompiles. So it's going to get a little bit more complex. Browser's starting to lag a little bit. So there's our first decision point, and then we've got our second decision point, the fragile label. And same kind of thing. Slowest processed, medium slow, and fastest. And then all of these items will now, if we did our work, have a fragile label right there. If you can see it. So everything's got a fragile label now. Now, finally, for our shipment logic, we're going to check, this is pattern matching again. If it's true for hazard and true for fragile, we're going to group it as fragile, hazard, fragile, etc. Put those into different flows, and then this is the shipment logic. And this has a nice real-world implication. Like if you want to batch things up and write them to a database, there'd be a good use for this kind of a pattern. But this group within operator is kind of cool. It will take 100 items and wait 4 seconds for them, and if it doesn't get 100 by 4, it'll flush. So it's sort of like a way to do buffered bouncing. This is nice. And then we ship it using map async because that's an asynchronous process, and then we're just going to output what gets shipped. All right, and then we've got those 4 processes, and again, like anywhere, this graph is getting really big, and it'd be pretty hard to reason about where it's pushing and where it's pulling. and where the bottleneck is. And the nice thing is you don't really have to worry as much. I mean, if you have a deadlock and you shoot yourself in the foot like that, which you couldn't do like here because it's a DAG. If you're doing a DAG, you're fine, right? But if you had any circular dependencies in there, then you could have a deadlock. Yeah, it'll figure out where to push and where to pull. So we're gonna run the whole thing. Let her fly. And there we go. It's struggling a little bit. But there's our shipments. So each of the 4 piles for shipping items. And these numbers are lower because that's the number of groups it yields. But over here in the console, you can see each shipment. I mentioned the group within. So if it doesn't happen to get the full group within 4 seconds or whatever the threshold is, it'll flush it anyway. It'll send the ship or the truck off or whatever. Anyways, there we go. It's shipping. That is the end of my code demo. I hope you guys like that. Just kind of like a final thought is there really are a lot of uses for streams, and I don't want to encourage you know, now that you have a hammer, everything looks like a nail, that kind of idea. But I think it is a really good challenge to think about what problems you're working on and where this might fit, because there's some surprising cases where it's really useful. And like one of the things I love about Rich Hickey's talks, like have you guys watched the transducers talk? Yeah. I started the first 10 minutes and I was like, well, that's stupid. Cheese is on the top instead of the middle, right in the taco. Or like you gave the Mexican food analogy. It says it's the same thing, but it's just reorganized. Well, the transducers talk was like, at the end, I was pretty mind blown because he found a really general abstraction. And if you don't know what I'm talking about, I'm sorry, it might be a bad example. But with the transducers, he found a really general abstraction, which eliminates the need to re-implement map on every data collection out there, or reduce or filter. Basically, you can get every one of those with fold and a transducer with the right level of abstraction. And I think stream processing has potential in many areas of computer science where we're not using streams, and where it would significantly clean up our work. And one that I've just been thinking about earlier is HTTP server. So we all know that HTTP servers stream the responses, but can you model the response, the getting connections and closing them as a stream as well? And it turns out that's a really good way to model it. In fact, it works out extremely well. What happens if too many people are connected to a server at a time?
You can start dropping.
You start to drop, or you back pressure, or yeah, you have control over this. So if I have, and this is like real code, but the guts are like sort of fake, but it could be implemented, totally could. So stream TCP bind your server address and then connections. This gives you a stream of HTTP connections, which is boundless, right? So you just people connect and you're just stream processing them. It's kind of weird and cool. And then you can choose your strategy. How do you want to deal with being overloaded? Well, in this case, we could throw an exception if it's to 500 or something, or 503, or whatever it is. And then for every connection, we can open up that, which is a byte stream. Use a transformer. Scala has, or AquaStreams has this idea of the stateful transformer, which allows you to parse structured data as a stream. Like if you were looking for new lines and you wanted to yield a line at a time, but you had a byte stream input, you could use one of those to keep track of your last new line and your next new line, and then emit one string at a time. So that's a transformer. So you could totally pull that in a streaming fashion and wait till you have enough to determine what the HTTP header says, and then yield the rest of the content as a string. And then you could map it through your route and process the request. And then you could send that through another flow which handles serialization and sending it back to the browser. So kind of an interesting way. And this is actually becoming a reality. As part of the AquaStreams initiative, Akka is merging in a really great HTTP library we love at SpinGo called Spray. And so it just so happens that HTTP servers and streams, like streaming the connections and streaming the creation of connections, is a really great pattern, and they work well together. So this is happening. Yeah. Thanks, guys. I appreciate your attention.
You have time for a couple questions?
Sure.
Well,